Hi, today in Applied Calculus we're going to wrap up our curve sketching. So we're going to revisit that idea of partition numbers and see what happens if we're graphing a rational function. So a function that looks like a fraction and what extra things we have to consider if we're doing that. So we're going to use our same curve sketching strategy from previous sections. We're just going to add a couple things that we're going to check in the beginning first that we need to consider. So same thing as before, but we are going to have some extra parts where we are asked to find the x-intercepts, the y-intercepts, and then we'll include those on our graph when we get to the end. We'll want to find the vertical and horizontal asymptotes and include those with dashed lines on our graph at the end. And then when we are creating our first derivative table to check for increasing, decreasing, and eventually identify maxes and mins, we need to remember to put both the critical numbers, which is what you're used to, and those partition numbers. So even those things that we couldn't actually call critical numbers because they were not in the domain of the function, the reason they weren't in the domain of the function is because they end up being the location of vertical asymptotes. So I have actually put a simple fill-in-the-blank question on my test before and asked, what is the only difference in making your first derivative table for a regular polynomial and a rational function? And it is that instead of just having critical values as your dividers of your table, you will also have any vertical asymptotes. So you could either tell me critical numbers and partition numbers, just to stress those partition numbers that are not also critical numbers, or you could say critical numbers and vertical asymptotes, as I've underlined here. Either of those combos would be acceptable. And then similarly, in the second derivative table, we're not only going to put those possible inflection points, those things that were in the domain of f, we're also going to put any of those partition numbers on the table as our column dividers to check to the left and right, because those are locations of vertical asymptotes. So why do we do that? The reason that we put the partition numbers, even things that are not actual critical values or inflection points when it comes to the second derivative table, on there is because vertical asymptotes are places where increasing and decreasing can change. So yes, if you have a max, you change from increasing to decreasing, but also you could have an asymptote and have increasing and decreasing change. Now it's important that I know that this is not the location of a critical value, so I won't try to claim when my table shows increasing and then decreasing that that's a max there, because there's not even a point there. It's undefined there. But when I name intervals of increasing and decreasing, when I go to sketch the graph and know what it looks like, increasing and decreasing can change at a vertical asymptote. They don't always, but it could, and that's why we are still going to include those values on our table. Similarly, concavity can change at a vertical asymptote. So we can't actually say there's an inflection point here because it's not even a point on the graph. It's not even part of the function. It's undefined there. But when we talk about, oh, it got erased. When we talk about the intervals of concavity and we go to sketch it, we could have concave up and then it could change to concave down there. So we're still going to test to the left and right of those. So what we're going to do is we're going to work through two complete problems, and so it'll be yet again practice of finding critical values, doing the first derivative table, finding inflection points, doing the second derivative table, but we'll have the additional help of the x-intercepts, y-intercepts, and asymptotes at the beginning. So remember that the other part of the notes before you get to this is a review of how to find x-intercepts, y-intercepts, vertical asymptotes, and horizontal asymptotes. The latter two we have already now reviewed multiple times, actually. Okay, so this is what a real curve sketching of rational function will look like. So here's our function. It is a fraction. It has a fraction that has x's in the top or the bottom. And so the new questions that we'll have at the beginning are things about the domain, the intercepts, and the asymptotes. So that's what we're going to look at first. For domain, the things we need to watch out for with domain are division by zero and even roots of negative numbers. Well, we don't have any roots, so it's only the division by zero that we're worried about. So to find the domain, we need to see when the denominator would equal 0 and then leave those spots out. So what we're going to be talking about is, I know these are large problems that take up a whole page of work, but I give you cues along the way, and the fact that this is so many parts is actually a gift. Not to do a back in my day, but back in my day, I was told use curve sketching techniques to do this. And I had to know I better do parts A through I, that I just had to do all those things. So I am telling you all those things, and they should be cues in your mind. And so that's really what I want your focus to be, is that cue of what do I do next, and just do the next thing instead of getting overwhelmed by the larger problem. So domain, it's a fraction. We're worried about division by 0. You set the bottom equal to 0. So I have highlighted in red all those cues that I want you to be thinking as you do these. So we set the denominator equal to 0. It factors as difference of squares, and we get 3 and negative 3. So that means that our domain is everything but those. Okay, so remember, a lot of times students forget this interval. Remember that everything up until negative 3 is okay, and everything right after negative 3 until 3 is okay, and then 3 to infinity. So that's our domain. Next, we see x-intercepts. If you're having a hard time with x and y-intercepts, draw yourself a picture. I do sometimes. So an x-intercept, draw a picture. It means you're on the x-axis. If you're sitting on the x-axis, then you are not up or down at all, meaning your y is 0. So to find an x-intercept, we let y be 0. Well, a fraction is 0 when its top is 0. So I'd really be setting just 3 equal to 0, but there's no variables there. 3 will never equal 0. And so I will actually end up not having any x-intercepts. Now, we've talked about this before. Don't just leave this blank. Tell me you know that there are none. Right? Blank means I don't know, but telling me that there are none means you know that there are none. Okay, so then y-intercepts. Again, if you're having trouble mixing these two up, then draw a picture. So here's a picture. If I'm sitting on the y-axis, I am not left or right at all. And so I am letting the x be 0, right? If I'm not left or right at all, x is 0. So to find a y-intercept, I let x be 0. That's the simpler one. And so I just plug in a 0 for x, and I get negative 1/3. So that gives me the ordered pair 0, negative 1/3 as my y-intercept. Okay, next we have vertical asymptotes. And you hopefully were reviewing this before you got to this part of the notes as well. And with those vertical asymptotes, we're setting the denominator equal to 0. Now remember, if there were common factors that would have simplified first, we would have done that before setting the denominator equal to 0, but that did not happen here. So I set the bottom equal to 0. I've actually already done that. And what I get is 3 and negative 3. Why? Well, that's why those places are not in the domain, because there's vertical asymptotes there. So remember that an asymptote isn't an equation. So I do need to have x equals or y equals accordingly. In this case, it's nice because our work gives it to us, x equals. So those are our two vertical asymptotes, and we will sketch them into our graph. Lastly, horizontal asymptotes. Remember that you're looking at the degrees of the function. And so if I look, the degree of the bottom is 2 and the degree of the top is 0. If the degree of the bottom is more, then the answer is y equals 0. So I do need to remember the y equals part. So this is really the only part that is additional, and then we will have one change to our table. But the rest of the process is the same. So it's just actually all review concepts from algebra and pre-calculus of the domain, intercepts, and asymptotes that you will find that you are asked at the beginning of the question. Then we get to the same prompts we're used to seeing. Again, I want these to be cues going off in your head when you read the next part. So when you read critical values, you should think first derivative equals 0 or does not exist. Well, that means I better find a first derivative. So you could use the quotient rule if you'd like. It's not necessary, but you could. And so if we do use that, instead if we rewrite it, it can go a little bit quicker, but it doesn't matter. You should find that you get the same answer either way. So if I bring down my power, leave the inside alone, subtract 1 from the power, and then multiply by the derivative of the inside, I get negative 6x over x squared minus 9 all squared. So remember, I'm trying to see when this thing equals 0 or doesn't exist. Well, the derivative equals 0 when its top is 0. So a fraction equals 0 when its top is 0. And in this case, we do have a variable. So we're going to set the top of the fraction equal to 0, which is negative 6x equal to 0. When we divide by negative 6, we get 0. So we have a critical value of x equals 0. Then we look for the does not exist kind of critical values. So the derivative does not exist when its bottom is 0, right? When its denominator is 0. Well, its denominator is 0. I can square root both sides, and then it just gets back down to that same x squared minus 9. So it's a difference of squares, and it happens at negative 3 and 3. Well, remember, though, I cannot call something a critical value if it's not in the domain of the original function. And it's not. That's why we check domain first. 3 and negative 3 are not in the domain of the original function either, because in the original function, they also cause division by 0. So I cannot call those critical values. I will still look at them on my table, though. So the only critical value I have is this x equals 0. Oh, I got that. So x equals 0 is the only critical value. Now, our next step is going to be our first derivative table. So remember, we've seen these same parts. They just have different letters because we scooted them down the line. We are looking for local mins, local maxes, and intervals of increasing and decreasing. All of those can be answered with the first derivative table. So the second you find that those critical values and you read these next parts, your head should say first derivative table, okay? So remember, it's called the first derivative table because we're checking the sign of the first derivative, all right? So what we're going to do is draw our number line and put all critical values and vertical asymptotes on our number line. Remember, scale doesn't matter, but order does. So I need to put negative 3, then 0, then 3, and leave enough room to test to the left and right of each of those, okay? So I'm going to say what interval each one represents so that I can easily state my answers at the end without much thinking. And then I'm going to pick a test value that is strictly inside, cannot be one of the endpoints of the intervals, and then I'm checking the sign of the first derivative. Well, what I notice with this particular first derivative is that the bottom is squared, and so no matter what I plug into that, the bottom's going to be positive. So I just went ahead and wrote that all my denominators are positive, and therefore the sign actually depends on the numerator. Well, my numerator is negative 6 times your value, and so when I'm plugging in negative values, I end up getting a positive. And when I am over here plugging in positive values, I end up getting a negative. So in these two columns, I get that the sign of my first derivative is positive. Then remember that why are we doing this? Because when the derivative is positive, the function is increasing. And that happens for both of those. Then over here, I end up getting a negative sign when I plug into my first derivative function. And when the derivative is negative, the function is decreasing. And so that happens both of these places. Now, I like to label where these values came from. So you can see I said 0 was a critical value, but negative 3 and 3 were vertical asymptotes. And so when I see that increasing and decreasing changed here at x equals 0, that really is the location of a max because it really is in my function. And I just want to be careful not to call something that isn't in my function a max or a min of that function. So it does look like I have a max here. And then but I don't see any mins, right? I don't have any places in the domain of the function where we change from decreasing to increasing. So again, don't leave it blank. Say that there are none. So there's no mins. And then if there is a max, then that's when we'll take the time to plug our x value into the original function to find the y. So we plug into the original to find the y, and we get the ordered pair 0, negative 1/3. So that is our local max. Then intervals of increasing and decreasing, I'm just going to read right off my table. No, you should not smush this to be one single interval because it's not. Negative 3 and 3 are not in the domain of the function, so they can't be in the something describing the function, an interval describing the function. So for increasing, we had from negative 3 to negative 3 and negative 3 to 0. and then decreasing 0 to 3 and 3 to infinity. Okay, and we have now accomplished those parts. So again, local mins, local maxes, increasing and decreasing are all accomplished with the first derivative table. The next part you would read is possible inflection points. So remember that we don't have two different words in second derivative world, right? In first derivative world, we have critical value, which means a possible max or a min, and then if it turns out to be a max or a min, we call it that. In second derivative world, we don't have two different names, so we just have that it's a possible inflection point, and then if concavity actually changes there, then we say it's an inflection point. But I want this still as a prompt for you because I want it to be one of those keyword items, that when you read possible inflection point, you think second derivative equal to 0 or does not exist, so that you know what your next step is. Your next step is, well, if I need to see when the second derivative equals 0 or doesn't exist, I better find a second derivative. And so that's what we're going to do here. So remember what our first derivative was. Our first derivative was a fraction. Now this time, because it has x's in both the top and the bottom, I don't really feel that rewriting it will be any less work. You could do that and use the product rule instead if you would like, but I'm going to use the quotient rule. So remember to go back to what you already found as your first derivative and then do the derivative again to find the second. So here, I'm going to do bottom times derivative of the top minus top times derivative of the bottom, and I have a chain rule here. It keeps changing on me. And then in the bottom, I have the bottom squared, okay? So there's some simplifying that we can do because remember, if we're going to take this fractional item and see when it equals 0 or does not exist, then we need it in a pretty simplified form. So whereas in the past I said I'm not going to make you simplify it if it's not going to accomplish anything, if that wasn't the point, but that eventually we would need to, and we're there now. All right, so I'm cleaning this up a little bit, and the negative times the negative gives me positive, and the 6x times a 2 times a 2 ends up giving me 24x squared. Right now I have two terms, two big terms, which each share a factor that I've underlined in red. And so that factor can actually be factored out in front. They also happen to have negative 6 in common. It doesn't end up mattering if you factor that out or not, but just to follow our standard, you should factor anything you can, then we'll do it. So they both have negative 6 and one copy of x squared minus 9. So I'm factoring that out in front and then putting a big parentheses, and remember factoring is a form of division. So what I'm putting in the parentheses is what is left in each term when I divide by that. So when I divide this first term by negative 6 times one copy of x squared minus 9, I'm left with the other copy of x squared minus 9. When I divide my second term by negative 6, so it was negative, so I'll have a minus. And then that copy, that's the only copy we had here. So then we are left with the negative 4x squared. Then the reason we did that is because by factoring out a copy, I can cancel it with one copy in the bottom. And so now I actually just have cubed in the bottom. And in the top, I have a negative 3x squared. And I guess I ended up putting my negative back in, so sorry. But what I wanted to show you was that this didn't end up looking like a difference of squares. And so instead of having a negative negative, and then another negative out here, I made it all positive. So it turns out there's one more 3 that can come out. It doesn't actually matter, but just to be thorough, I have completely factored it, and I have 18 times x squared plus 3. And what we're going to see in a minute is that the fact that that's x squared plus 3 and not x squared minus something is going to be kind of key. So this was just the quotient rule, but we are actually having to do a little bit of factoring now, where when there is a common factor to be taken out, we need to do so and cancel because we need our numerator and our denominator to be as simple as possible and written in a factored form so that we can set each one equal to 0 and find those possible inflection points. So to recap, this is what we found for our second derivative, and we're trying to find when the second derivative equals 0 or doesn't exist. A fraction equals 0 when its numerator equals 0, and it doesn't exist when its denominator equals 0. So when we look at the numerator equaling 0 and we actually go to solve it, we can divide by 18, we can subtract the 3, and then I'd be ready to take the square root of both sides, but I'd be taking the square root of a negative number. And we're living in the real number world here, and I would need imaginary numbers to do that. So there's not going to be any places, any real values of x that will make the top equal 0. So I won't get any critical value, or inflection points that way. Then I need to see when the second derivative does not exist. Well, it doesn't exist when its denominator equals 0. So I set the entire denominator equal to 0, but then I would just cube root both sides, and I'd be back to that same x squared minus 9 equals 0, which I know factors as a difference of squares and gives me 3 and negative 3. But 3 and negative 3 are not in the domain, so if they're not even in the domain of the function, they can't be a feature of the function, right? They can't be an inflection point of it. So they are not possible inflection points. So back on the part where you were asked for possible inflection points, you would write none, okay? That doesn't mean that I don't have anything to do on my table, though. So I get to the last questions, L and M, which ask for intervals of concave up and concave down, and that should trigger in my head second derivative test. So really, when I hit that possible inflection point question, the point of that is to trigger you just to go into second derivative mode altogether, right? We found those possible inflection points, and then we're going to do a second derivative table. So again, I didn't actually get any inflection points, but I need to put any inflection points and vertical asymptotes on my table. And so I did have vertical asymptotes, and they need to go there. So my table is a little bit smaller because I don't have that extra piece. I just have negative 3 and 3, so I have 3 regions to test. Now, in this case, the top will always be positive because I'm squaring something to make it positive, then adding it, then multiplying by a positive. So the top will always be positive, and the sign will actually depend on the bottom. So I'm going to name my intervals, pick test values that are strictly inside of them, and then plug into the second derivative because this is the second derivative table, and because the second I saw possible inflection points, I shifted into second derivative mode. So make sure you are plugging into the second derivative. And so I end up here with positive, and remember, when the second derivative is positive, the function is concave up. When the second derivative is negative, the function is concave down. And so I end up with concave up, concave down, concave up, and I would summarize that. So concave up would be negative 3, negative 3, and 3 to infinity. And intervals of concave down would be negative 3 to 3. So we have done all the parts of the question, and now we're actually going to put it all together and graph it. So we've had to do it on multiple pages so that it's big enough for you to see, and I'm going to have to kind of reference back to all those things to graph it. So what we want to graph is any x or y intercepts, and we did have one of those, any vertical and horizontal asymptotes, and then show any maxes or mins and make sure that our increasing, decreasing concavity all shows up there. So if I ever ask you to graph on an assessment, I will give you a nice grid to do so. And so let's think about some of our features. So we had those vertical asymptotes at negative 3 and 3, and I am just counting by ones here. So there's my vertical asymptote at negative 3. I'll do one at 3. We also had a horizontal asymptote of y equals 0, right? Because we had, yeah. So we had y equals 0. Okay. And then the only point we had was our 0, negative 1/3, and it ended up being a max. Then we have to rely on our tables. Again, you would have all this kind of on one page and be able to look back at it. But what we found was that we had increasing from our first derivative table and concave up from our second derivative table up until negative 3. So if you remember that we have to follow along asymptotes and not cross through them, like kind of ride alongside them, and I have to increase and be concave up, I can't do that here because I'd have an issue with this asymptote. So the only way to be increasing and concave up is for me to draw up here. Then from -3 to 0, we still had increasing, and then from 0 to 3, we had decreasing, but in that whole interval from -3 to 3, we had concave down. Okay, so we had increasing concave down and then decreasing concave down. Increasing concave down to hit that max. Decreasing concave down, all right? And I'm riding alongside our asymptotes as we go. And then lastly, we had decreasing and concave up, if you look at the two tables. So again, if I'm going to decrease but be concave up and be following asymptotes, I need to be up here. You'll see it just won't look right. It won't follow asymptotes if I do it down there. And I'm not generally supposed to cross this. I'm supposed to ride alongside it. And so that would be my complete graph. So I am supposed to show the asymptotes, any intercepts, and any maxes or mins, and then make sure that it all checks out in terms of increasing, decreasing, concave up, and concave down. So let's look at one more complete problem just to see what can happen. All right, so this time we have x plus 2, x minus 2, and let's practice with those mental cues. So domain, I'm dealing with fractions. All I'm really worried about is division by 0. So denominator equal to 0, that happens at x equals 2. And so that's not in the domain, and my domain is everything but that. Then x-intercepts, if you need to draw yourself a picture, go for it, and then remind yourself that that is when y equals 0. So we said y equals 0, but it's a fraction. A fraction is equal to 0 when the top is equal to 0, and that happens at -2, so we have the point -2, 0. Then y-intercepts, draw yourself a picture if you need it, but that's when x equals 0. So we plug in a 0 for x, and when we do that, we get 2 over -2, which is -1. So I have the point 0, -1. Do think about the order of your ordered pair when you're stating them. Then for vertical asymptotes, denominator equal to 0, we've actually already done that work, and that happens at x equals 2. So we have a vertical asymptote at x equals 2. Then for horizontal asymptote, we're looking at the degrees. This is the nice case where they have the same degree. They both have a power of 1, and so it's the ratio of the leading coefficients, which are hidden ones, and so it's y equals 1. And that's it. So I know I had some pre-written here, but that's because if I'm writing and talking, it would have taken me longer. Just because this is a big problem, it does not have to take forever, right? If you have those mental cues down, you can whip this out real quick. All right, so then the next part would say critical values. What should happen in your head is first derivative equals 0 or does not exist. And so that means I need to find my first derivative. It's a quotient rule problem. Bottom times derivative of the top minus top times derivative of the bottom, all over bottom squared. I do need to simplify, and I get -4 over x minus 2 squared. So I need to see when it equals 0. A fraction equals 0. When its top is 0, there are no variables there. It will never equal 0. It will always be -4. So I get no critical values there. Then the derivative won't exist when the bottom is equal to 0, but the bottom equals 0. I can square root, and I'm back to x minus 2 equals 0. I get x equals 2. That is not in the domain of the original function, so I cannot actually call it a critical value. It will still show up on my table, but it is not actually a critical value. So your answer to part F that you would write over on that side of the page is that there are no critical values. Then you would get to G, H, I, and J, which are the maxes, mins, increasing and decreasing, and your brain should say first derivative table. And we're in first derivative mode because we were just finding critical values. So I did not have any critical values, but I do have a vertical asymptote. So I'm going to put that vertical asymptote on my number line, leave room to the left and right to check the sign of the first derivative. All right, so I plug in this case, the bottom will always be positive, so it just depends on the top. But actually the top will always be negative because it's just a constant. But anyway, as you plug in, you'll see you get negative, negative. Well, when the derivative is negative, the function is decreasing. And so I'm not going to have any maxes or any mins, and I'm not going to leave these blanks. I'm going to say, I know there are no maxes or mins. And then intervals of increasing, also none. And then intervals of decreasing, I do need to separate them out as they are already. I'm just reading off my table. So we have negative infinity to 2 and 2 to infinity. So I wanted to do one example like this for you because when you get to this one, it's actually pretty simple in terms of the algebra involved compared to others, but people start freaking out that they must be wrong because they're getting all these nones and nevers, but it can happen. So I wanted to show you one where you got a lot of answers for a lot of the problems, and then one where you got a lot of nones and nevers and tell you that it is okay and you are doing it right. So then I would see possible inflection points. My brain will shift to second derivative mode. Possible inflection point, second derivative equal to 0 or does not exist. That means I need to find a second derivative, so I first need to recall my first derivative, and it is here. In this case, again, if there's a constant in either the top or the bottom, but here the top, then I do think that rewriting it and using the chain rule is quicker than using the quotient rule, and so I have done that. And so here's my derivative. I get 8 over x minus 2 squared. Remember, I didn't forget the derivative of the inside, it just was 1. And so then I'm seeing when this equals 0 or does not exist. Well, a fraction equals 0 when its top equals 0. There are no variables here. Its top is always 8. And so I don't get any of that kind of inflection point. Then I'm seeing when the bottom is equal to 0. Well, if I set the bottom equal to 0, I would cube root both sides, and I am back to x minus 2 equals 0, which we've done before and gives me x equals 2. However, I cannot call it an inflection point of the function if it's not even in the domain of the function. And so this is another none, all right? So up here, possible inflection points, I would write none because I am going to have a vertical asymptote but no inflection points. So then you get to L and M, the last couple questions, and we're looking at concavity. Remember, the sign of the second derivative tells us the concavity of the original. Also, we shifted into second derivative mode when we did possible inflection points, and so we are using the second derivative table. Didn't have any inflection points, but I still need to put vertical asymptotes there, and then I need to check to the left and right, and the top is always going to be positive 8, but I need to look at the sign of the bottom, and I end up getting negative for this first interval. When the second derivative is negative, the function is concave down. When the second derivative is positive, the function is concave up. Then lastly, so I need to summarize that. So concave up, 2 to infinity. Concave down, negative infinity to 2. So I would write that in. And then on the last page, or the last part, if you're asked to graph it, then that's what we're going to do. Again, that's actually easier to do when you have it all on one nice page, but we got to go back and think what we had. So I know we had a vertical asymptote at x equals 2. And we had a horizontal asymptote at y equals 1. And then we had some intercepts. We had negative 2, 0, and we had 0, negative 1. Okay, so then we have to think about all our concave up and concave down and increasing and decreasing. And we had decreasing and concave down in that interval. If you go back and look at your tables and what we summarized. And we had decreasing and concave up over here. And so if I go to put this all together, use a different color, then if I need to follow asymptotes, hit these 2 points, be decreasing and concave down, there's really only one way I can draw it. Okay, and then over here, I need to be decreasing and concave up. I can't make that shape and follow asymptotes down here. And so to be decreasing and concave up and follow asymptotes, then I need to be up there. We can also do like a test value in the original function in each interval to see where we should be, like above or below the axis. but usually just following everything we've already had to do helps us to draw it correctly. But again, you can see that just knowing increasing or decreasing wouldn't have been enough because the concavity affects obviously what it looks like and how then could it follow asymptotes, and so it really does help to give you the whole picture. So remember that you will only have a scientific calculator, not a graphing calculator. And so I know that online you could crank through some things by just pulling up the graph and reading off of it to answer those questions. But this will be a large portion of your test. This will be a 24 to 25 point question where you have to do all these parts we've talked about. And so it's really important that you actually take the time to practice the steps and use those mental cues that each part gives you as we've discussed. So I hope having 2 more complete curve sketching problems, these just having the addition of intercepts and asymptotes and domain, and then the table possibly having both asymptotes and critical numbers or inflection points as appropriate. But it really just the overall process, it's just yet another practice for even problems that don't have the rational issues in it. So that's going to be it for curve sketching. Again, there's review in your notes in addition to what I've done here. But I wanted you to kind of see that it doesn't have to take you forever, that if you have those mental cues down, you can just knock it out one by one, and that it does come all together to help us understand what the graph looks like and how it behaves. So we're going to be shifting into absolute maxes and mins next time.